My name is Amanuel Gebremeskel. I'm the technical director at the Institute. That job basically entails taking care of all the various technical aspects that we address at the Institute. We have a number of publications. We'll talk about a few of them today. We also support the industry, and what that means is essentially the steel industry, but also engineers, architects, and other people involved in construction with technical assistance. And in fact, these events that we're carrying out or holding every Wednesday are meant to sort of share what we have learned from these types of services that we provide, where people ask us questions and we try to find the answers. We try to find experts in different areas. I hope today we'll be able to share some of the issues that have come up from both consultants and the industry, and see if you find them of interest. And I hope, of course, that you'll also be able to contribute.
Fantastic. So also with these sessions, what we do is we try and have them up on our YouTube page within 24 to 48 hours. So if you want to go back and go through some of the content that was covered, that's great. We'll also be breaking up the questions into smaller videos and putting them on our frequently asked questions playlist. So, right, I think let's just give it a minute or so. We'll get going as we hit 1 o'clock. Oh, we just hit 1 o'clock and we're nothing if not punctual at the Steel Institute. So, Emmanuel, do you want to maybe just give a little bit of an introduction to the session today? We're chatting about Purlins and Girts. So, brief intro, Purlins and Girts, what are they? How are they used? Give us the rundown.
Okay, yeah, so some of these terms can be confusing. These are somewhat technical terms that may mean different things to different people. But just to explain it in general, if you look out your window and maybe look at a tree, if you have a tree outside of your window, then what you'll see is a big trunk, off of which you'll have some limbs that come off of the trunk. And off of those limbs, you'll see branches, and finally, you'll see some twigs. So nature is one of the best structural designers, in that it's every single part of that tree is actually well proportioned. So the trunk is essentially the biggest, fattest part of the tree. Then it gets to become a smaller diameter when it's the limb, smaller in the branches, smaller in the twig. And of course, this is a very efficient design to carry leaves, which is the ultimate goal, because the leaves are required to pick up sunlight and produce food for the tree, right? That's the whole point of the tree, is to create the structure to carry leaves. So in a similar way, if you look at how old huts are built for dwelling, then you'll have the middle post, and then you'll have posts around the perimeter of the hut, which have a ring beam on top, and then you'll have rafters that connect the middle post to the ring beams. And then in between those rafters, you have to put something in there that's going to pick up the thatch roof, because the thatch roof can't span from one rafter to the next. It's just too far apart. So those are typically called purlins. And what that basically means is it's that element, one of the smallest structural elements that you're going to have in a building, to pick up the final cladding, whether it's thatch or whatever kind of system you're using. If you look and open your ceiling in your own house, you're going to find the same thing. You're going to have trusses. And in between those trusses, you'll have those small little pieces of wood, which carry your tiles, your steel sheet, whatever kind of cladding you're using. Those are also called purlins. Now, if you look at the side wall, most houses in South Africa are actually made out of brick walls. But if you go back to the hut, you have those posts on your side wall. And between those posts, again, you will need some sort of member to pick up the side, whatever it is, whether it's made out of mud or clay, to carry those. And those are called girts or side rails. So this is essentially the nomenclature for construction of dwellings and large buildings. And we haven't really changed the naming as such when we go to large industrial buildings, where you'll have the same technology employed between the rafters to pick up the roof sheets, and between the columns to pick up the side sheeting, which is essentially your side cladding. And those members in the roof would be called purlins, and the ones on the side would be called girts or side rails.
Fantastic. Okay, so my next question, what materials and shapes are used to manufacture purlins and girts?
Okay, so if you think back to your hut, typically it's made out of wood. It can be different shapes of wood. Sometimes it's just natural wood of thin diameter that's used. If you think to your house, again, it will be nicely shaped squarish or rectangular wood that will be used for purlins. But when we get to larger industrial type buildings, typically we make use of steel purlins because the spans are much longer between rafters. We're talking about spans of 4, 5, 6, 7, 8, up to 12 meters. I've seen purlins that can span that long. And these steel members are typically made out of very thin materials because, of course, the idea is to make savings, just like the tree. How each twig is much thinner than the trunk. The same thing here. We want the thinnest members for purlins and girts. And when I say that, I'm talking about thicknesses of, let's say, anywhere up from 1.5 to 2 millimeters, all the way up to maybe 3, 4, 4.5 millimeter thick material. The material itself can come in different forms. It can be what's called commercial quality steel. We can discuss what that is maybe a bit later. It can be graded steel. It can be pre-galv. It can be galvanized in a hot bath of zinc. It can come in many different varieties, but the shapes will typically take the form of, let's say, C shapes, channels, or sometimes Z shapes, sometimes top hats, which are essentially like, let's call them C shapes that are facing down, sometimes angles. I've seen purlins that are made out of angle shapes, which is essentially an L shape. So we have many different types of purlins and girts that we use in industrial applications, but in homes and other smaller applications, it's typically made out of wood. But more and more so these days, of course, steel is used also in homes, just because it is more, you can recycle it, you can use it, and economically also it's much more durable, right? Because in your house, you don't have to replace it. It doesn't get attacked by termites and moisture as much as you might see for wood.
Just Emmanuel, from my side, a question that we hadn't discussed yet. I know that I'm not sure if John Barnard is in with us here, but in the various applications, if you're looking from a smaller kind of setup going into your bigger industrial setup, on the smaller side, what would you say the advantage would be of using something like light steel framing versus wood in purlins and girts?
Yeah. So if you're referring to roofing now, which is what purlins go on roofs typically, then of course, when you're building a house or if you own a house, you have a choice. And typically your choice in South Africa are between wood truss and purlins and steel truss and purlins. Now, sometimes it just comes right down to cost, but in many cases, it also comes down to longevity, meaning how long can you actually have that up without having to fix it up, restore it, or replace it. And in that sense, the steel is advantageous. The second area where steel might be advantageous is if you have much longer spans. And that's what I referred to earlier. So if you have these very nice fancy houses these days where the owners don't want walls in between in their kitchen and living rooms, and this is these combined nice big spaces, then of course you're going to need pretty long roof trusses. And of course, if you're going to use a steel roof truss, it's going to have a lot of capacity as compared to a wooden truss. And then the implication of that is that you're going to space those roof trusses further apart. Now, when you do that, you're going to need purlins that can also take the load between trusses that are much further apart. And then again, that makes you essentially, in a way, forces you to use steel purlins. So there's much more architectural freedom when you're using steel trusses and purlins as opposed to wooden trusses and purlins. So you can look at it both from a point of view of durability and from an architectural freedom point of view. The third area, which is still being studied by many countries around the world, is this issue of green. So what is more sustainable? Now that the steel can be very sustainable if it's recycled. Now, of course, the question of whether or not the steel that you're using is recycled itself is a big question. But in many markets around the world, in Europe, in the US, structural steel now is almost 100% recycled. In South Africa, we're not exactly in that kind of ratio, simply because we have a ton of iron ore. The world still needs a lot of steel to be produced. So in that sense, it's a bit of an unfair comparison. But in one way, using steel products can be an extremely green process, simply because you don't have to actually go and do new mining and take up a lot of energy to go and process the material. And of course, things like purlins and trusses, sometimes you don't even have to recycle them. You can just reuse them. What that means is you can recoat them, you can take them down, recoat them, and reuse them, which we've seen some very incredible projects. I don't know if you remember, Denise, from a few years ago, where they moved an entire warehouse, and I think it was an Anglo project, and moved it from one location to another and completely reused everything, including the sheets. So in that, that is absolutely green in every sense, meaning you have not had to use anything new. You just have had to redesign everything and use sophisticated contractors.
So, Amanuel, in terms of what's available for designing purlins and girts, what kind of resources are available to engineers in the design phase?
Okay, so a lot of engineers are very nervous about designing things that are very thin, and for good reason, because these types of sections are vulnerable to what we call torsion, which is like twisting type of failure modes, and also what we call local buckling, which is buckling that occurs within the section. So for those who are engineers on this call here, that would be essentially, most of these purlins would be like class 4 sections and girts. What that means is they're very thin and slender, so they have a high propensity to buckle. Now, we do have a national standard that you can use to design these thin types of steel members, and it's called SANS 10162 Part 2. A lot of people don't have it in their office and don't use it simply because they don't design these things. But because it's a bit complicated to use, what we have is a whole chapter in the Red Book that simplifies and summarizes what's in that standard for the purpose of using the information just for purlins and girts. So the Red Book, I would say, is probably the most used resource for the design and detailing of these purlins. We also have a yellow book, which shows a great deal of information on how to detail industrial buildings in general, but also the purlins and girts. And if you have the, in fact, I have to say, if you have the latest Red Book, which is the 2016 version, I've actually added a table in there, table 8.3, which is meant to be even more helpful. And we can talk a little bit more about the differences in the tables, but it's essentially a full solution for purlins that took a while to develop, but it is published in that Red Book. So there's quite a few resources out there, all the way from SANS standards to the Red Book to the Yellow Book. And there are a number of software vendors out there also who claim that they can design purlins and girts, or they can, meaning they're tools for engineers to use.
I see that Dennis's mic is unmuted. Dennis, did you have a question? You want to just pop your video on so that we can see your lovely face?
There we go. Yes, I have a question. With the advent of these very thick blankets, soft blankets of insulation, and if one views what is coming in the future edition of 10400XA, where you could have a blanket up to 120 or 125 millimeters thick, and you then have to couple that with a spacer system, which means your roof cladding is 120 or 125 millimeters above the surface of your purlin, you are getting some rather difficult torsional problems. How do you overcome that?
Yes, so you're diving right into the very important detail. Now, the way purlins are designed is you have to assume that there's cladding on them, of course, because that's the source of the load on the purlins, and it's the same thing for girts and side rails. The question of how the cladding is attached to the purlin is extremely important, because the purlin itself may or may not be braced by the cladding. Now, historically, we used to assume that the purlin is somehow restrained by the cladding itself from torsional movement. So if that's the purlin and that's the cladding, we assume there was a positive attachment between the two that prevented the purlin from rotating, twisting. And that was very helpful in our design. But these days, Dennis is bringing up a very good point, which is these attachments may not be direct. There may yet be an intermediate attachment method for a conceal fix type of attachments, or there may be insulation and a long gap between the purlin and the sheething with something in between that's not necessarily torsionally stiff. So when I solved the problems for table 8.3, which is the table I was just referring to in that red book, I actually assumed that the cladding does not provide any restraint to the purlins. So, and because now there's a second reason why I make that assumption. The second reason is these purlins can sometimes be loaded down, which basically means if the roof is being loaded down by wind or someone walking on the roof, same thing for a side rail and girt. But typically the design loading that controls the design of the purlin is what's called wind uplift, which is when the roof is being sucked up, which is what actually happens when you have these high velocity winds, what you see in Mozambique or other places, is when wind passes over a roof, it actually sucks up the roof. So it doesn't load it down, it actually pulls it up. And in that case, the purlin is being loaded up. So that compression flange, which is that bottom flange in that purlin, does not get bracing. So Dennis, I'm glad you bring it up because it also lets me maybe explain something about the table in the red book, that it does not assume that flange that wants to twist is actually braced by cladding. And it may very well make sense to ignore such assumptions of bracing in purlins if you're unsure of how the cladding is going to be attached to that purlin. Good point, yeah.
That's great. I just want to also remind everybody that if you have any questions, feel free to pop them in the chat, or if you're comfortable putting your video on and you can ask your question to Amanuel in person. Dennis, did you want to add any further comments on Amanuel's response?
Yeah, I've got a second question, and that's the straining wires that have to be attached to the eaves purlin and the ridge purlin at approximately 300 millimeter centers, which are tensioned, which is adding additional torsion to the cowl-form sections. How do structural engineers account for that?
In my experience, they ignore them. And not only do they ignore those forces, there are a number of other forces that are also, I notice, ignored. Now, that doesn't mean every engineer ignores them, but that are typically ignored. And the other one is forces that are transmitted from the gable end of a building to the braced bay of a building. Now, typically, most engineers do not provide for an alternative load path to get wind loading from gable ends to the braced bay. And that basically means that they're making use of the purlins as a way to transmit that force from a gable. So what is a gable end? Just so that I can have clarity here. So if you think of an industrial building, which is typically quite long, then there's the side of the building, and then there's the gable end, which are the two ends where you actually see essentially the portal frame shape, right? That's called, or if you think of a plane hangar or something, that's the side where the plane would enter typically, that's not always the case. So typically the way that we're not discussing bracing of industrial buildings here, but there will be a braced bay that is, let's say, further away from the end of a building. Sometimes it could be at the end of the building, but typically not. So if you have wind loading on a gable end, you need to transmit some forces of that wind back all the way into the middle of the building where the braced bay sits. And purlins are also loaded by that wind, which is typically not addressed. So Dennis, there are a number of, I think, forces that are not designed. I would say the most typical reason for not designing them by engineers is simply that they don't know how to design them. Because like I said, people are very wary of going and opening SANS 10162 Part 2 to check torsions and axial capacities of these thin member shapes.
Super. Okay, next up, sag bars. Tell us about sag bars, Amanuel. What's the purpose?
Okay, so this is somewhat related to Dennis's question also on design of purlins. So both purlins and girts are typically loaded in flexure. What that means is that they're loaded in their major axis in bending. And the typical mode of failure for most purlin shapes in flexure is what is called lateral torsional buckling. which is essentially a twisting of the member before it fails. So sag bars have two purposes. One is to try to prevent that purlin or girt from actually twisting when being loaded in flexure. Now, whether you need that sag bar or not is a design feature. But a second, more practical need for that sag bar, as its name implies, is to prevent essentially primarily girts, which are on their side, on the side wall, from actually sagging between the columns. So it's essentially a way of keeping them up, just holding them up so that they stay horizontal. And you need, of course, a sag bar that attaches to every girt, because all of them have to be kept up. And at times, some of my students, when I teach a course at WITS, forget that the sag bars themselves have to be tied to something at the end, right? Because otherwise, they're all going to sag together. So those ties are also very important, in that the sag bars have to be tied to either the eaves beam and columns, or be supported somehow at the bottom, at the foundation. And the same is true for purlins, which are typically on a rafter that's at an angle. And of course, those can also sag simply because they are sort of at an angle of that type on a roof. And the sag bars also provide restraint for purlins from just moving and sagging between the rafters. So sag bars have two purposes. One is to provide what is called restraint against lateral torsional buckling. And the second purpose is to prevent purlins and girts from sagging. And we have a number of interesting pages in that chapter 18 in the Red Book, talking about typical sag bar spacings on purlins and girts, because that drives the capacity of the purlin and the girt. So if you go back and look at my table in 8.3, you'll see that it relies on an assumption of a sag bar spacing to be able to give you the solution. So sag bars are very key. They must always need to be there in most industrial building applications, unless the rafters are very closely spaced. And they need to be tied to something to work to prevent the sag of purlins and girts.
Any questions? Anybody? Don't be shy. Pop your questions in the chat or put your video on and you can ask a question. Amanuel, I just wanted to touch a little bit more on wind loading. What are some of the common questions that come up, technical questions that we've received at the Institute related to wind loading?
So in the past few years, the most important, I would say, question that has come up relates to the load factors for wind loading. A bit of a controversial topic because the load factors for wind loading have gone up from what used to be 1.3 to 1.6. Many engineers are actually not aware of this, but this is indeed the case now, and has been so, I think, for well over a year now. These factors are found in SANS 10160 Part 1, or I think, yes, that's where these load factors are found. And that change happened, and it was missed by a lot of engineers. And it created quite a bit of heartache because, of course, that's quite a bit of change for how you design. So I would say the most typical and most, let's call it controversial question that comes up is this change in wind load factors. Now, the implication of those the changes in the wind load factors. Now, the first question is, why did they change? Why they changed is because there's been a great deal more work done on reliability, which is essentially, let's call it a statistical approach to try to calibrate the wind loading that is applied in South Africa to other countries, to the general global standard. And that was found to be wanting in terms of load factors. That's the first part. The second part is that this was actually, let's say, the reason why it was required has now been published in journals like SAISC journals. But at the time that it came out, these journals had not been published yet. So this is actually why a lot of the problems arose, as in people didn't know why these things have changed. And as far as the implication goes, of course, the loads are higher, but there are also changes in the wind maps that have also been somewhat missed. And if you combine the increase in the load factors, plus the changes in the wind maps, plus a few other changes, the effect on most buildings is actually not huge. But on light steel buildings, such as industrial buildings, there is an effect. So this is not going to be a non-event in the sense that engineers do have to pick it up and start designing to these new load factors. So I would say that's the main thing that comes up, the most controversial thing. The other things that come up, and Dennis might even know more about this than I do, is of course, whenever there's failure, people want to know why things failed. And of course, roofs do fail. I would say not infrequently. For anyone who's been involved with what's going on in Mozambique now, there have been a number of failures of roofs at Purlins and Girts from the event that they had last year, or this year actually, earlier this year. So I would say wind is a very important thing to design for. And the design of Purlins and Girts for wind is also extremely important. So the third thing that comes up in technical questions is how to understand what loading to apply onto Purlins and Girts. Because the loading that you apply on the cladding is not the same as the one you'd apply on Purlins and Girts. And that loading is not the same as the one you'd apply on rafters and columns, because this is all probabilistic. So the smaller the area that you're dealing with, the higher the load that you have to deal with, because probabilistically, the chances of a high load on such a small area is good, is higher. So these are all very much, let's call them source of confusion, where we get a number of questions relating to wind.
I see we have a question from John Swallow in the chat. Thanks for that, John. Yeah. He says, would you comment on whether the knee stays to trusses or rafter stabilize or destabilize purlins?
Aha. Yes. So this question relates to initially rafter design. So remember, those rafters are the large members, the limbs, let's call them, that carry the purlins. Now, those rafters in of them themselves are typically made out of I shapes, which, when you load in flexure, are also vulnerable to lateral torsional buckling, just like the purlins. And what we do very commonly is we go and take let's call it the bottom flange of the rafter. So the purlin typically sits on the top flange. And take the bottom flange of the rafter, we try to brace it from twisting by putting a knee brace between the bottom flange of the rafter and the purlin that sits on the rafter. So it's a clever and efficient way of bracing rafters. Now, the question that comes up is, what is the effect of that knee brace on the design of the purlin? Unfortunately, John, this is yet another area that is neglected. And of course, that is wrong to neglect it, because there is a force that is imposed from the knee brace into the purlin. And that force can be calculated. Now, I actually cover that in my course on industrial buildings, because it's what that knee brace is what provides stiffness to the rafter. And of course, to provide stiffness, it means it has to be loaded. So the load that comes from the knee brace into the purlin imposes a flexural force into that purlin. That has to be accounted for. But depending on how it's attached to that purlin, it can also provide it with restraint from lateral torsional buckling. So sometimes it might be legitimate to neglect that force if you can once or twice at least calculate and figure out if these things balance out. So this is something that requires an exercise at least once to check what the effect of the knee brace is on purlins, because it has both a loading and destabilizing effect and both a restraining and stabilizing effect, depending on the connection between the two.
Thanks for that, John. Reminder again, everybody, I love asking questions, but if you have any questions, you can also ask them. Thanks for that, John. Amanuel, okay, we've got a question from, thanks for that, Jermaine. Thanks for that prompt response. The question from Jermaine is, many engineers use the knee brace from the trusses to reduce the purlin effective length. Was that just a comment?
Okay, yeah. No, it's a question. I see a question mark. So yes, engineers do that. Now, when you do that, the way to tie that into John's question, in my view anyway, is if you reduce the effective length of the purlin because somehow you assume that knee brace is bracing that purlin, then most certainly you have to include the force from that knee brace into the design of the purlin, because you've already accounted for the benefit, which is the stabilizing effect. So in that case, you cannot neglect and ignore the force coming in from the knee brace into the purlin.
Yeah, so John's response to that was, some assume the knee brace provides vertical support to the purlin. So there we go.
Yes, now that is to me questionable, and the reason why I say questionable is because that load has to go somewhere. So if you take a purlin and you assume that the knee brace is providing vertical support, then that means the rafter is supporting the purlin in torsion, which is a highly problematic approach, because the rafter in torsion is still very soft as compared to the purlin in its major axis bending. So this is a stiffness problem. So I would question that approach, meaning the validity of that approach, unless you have a rafter that is very stiff in torsion.
Yeah. So I want to tie this back to one of our courses that's happening in September, which is our warehouse design course. Amanuel, can you give us a little bit of insight? What's been happening in warehouse design in relation to Purlins and Girts, and then maybe broader, what are some of the trends that you've seen happening in warehouse design lately?
So warehouses, of course, are becoming big, which is why we're running this course. So in the old days, we used to run industrial building courses with cranes and all these other things, because the majority of these buildings were used to manufacture things. That is no longer the case. There are still such buildings getting built, but that's not the main market. The main market is now warehousing, all the way from logistics, as in like things that we buy from China, India, and Asia, and transport and export into Africa, to things that we consume in South Africa, obviously, like with the big retailers. So that's why the course is now actually on warehouses. And of course, we talk a little bit about racking. We talk a lot about big roofs, because these warehouses are much larger than the old industrial buildings. But a few interesting things that have come up are things like data centers. These are essentially warehouses for computer systems, because of course, if you think of a company like Amazon or Google, they need big server banks all over the world, because these are essentially global companies that have services all over the world, and they need these big, let's call them big computer hubs. And when you build such buildings, there is an issue that you have to deal with relating to cooling and also effect of fire. So I would say fire in warehouses might yet be the next major thing, because I have seen a few questions come up. It's not something that we typically are used to dealing with in warehouses, because we always assume that there's no need for much fire protection on these purlins and girts, and of course rafters. So I would say that's one of the things that comes up, that I would say is an emerging area, which is the effect of fire in industrial buildings. The second one, and there are many ways of dealing with it. And I just want to say one thing: intumescent paint or some other form of sprayed applied painting on purlins doesn't work. Meaning it can work, but it is very expensive, because I saw one application of that in a project, and I was surprised. And the reason for that is because these purlins are so thin that they don't have a lot of inertia to pick up a lot of heat. So you would need a huge amount of protection on them to make it work. But the second thing that comes up, of course, which is not exactly necessarily related to purlins and girts, but is somewhat related, is the issue of racking, which also makes use of very thin gauge type of shelves, big shelves. And of course, the big problem that we have is that they collapse every so often and can be very dangerous in these modern warehouses, because they're quite big. So this is not exactly about purlins and girts, but it is somewhat related to industrial buildings that use purlins and girts. So I would say these two are sort of emerging areas. Another area that is more pertinent to roofs, which we've discussed in Dennis's talk, is the problem of flat roofs. As these roofs get bigger and bigger and bigger and bigger, we have to make them flatter and flatter to make the structure economical. And at some point, we're going to have to start dealing with the stiffness of the roof to avoid ponding instability. These are provisions we do not have in South African standards, because we didn't have flat roofs before, not many anyway. And I do cover that in my industrial building course, because other standards do include provisions for stiffness relating to ponding. Ponding is essentially if you have a roof that's kind of flattish, then you get rain on it, and then your drains get clogged, and it deflects down, and as it deflects down, it carries more water, and then it deflects down even more, it carries more water, and at some point it comes apart. So it's a stiffness problem. So it's no longer enough to just say my roof is good in strength. Now you may also have to start looking at the stiffness of your roof system, and that includes the purlins in that case.
Manuel, if you just want to quickly pop into the chat and check there, we've got some comments from Jack and from Don Garcia. In the meantime, while you're having a look and reading that, and you can perhaps just summarize what the question is, because I don't want to butcher any technical terms. But while Emmanuel's going through that, just our industrial design course, we will be releasing dates for that soon. So if you are interested, just pop me a direct message and we'll keep you in the loop when those dates are available. All of the other courses that the Institute is running are listed on our website under the training section. So some of our courses we've run in the first 6 months of the year, they will be repeating in the second half of the year. So there are some dates for those. And then if there are any other courses that are taking place, we do let everyone on our mailing list for these technical sessions know that they're happening. I will pop a link in the chat for those of you that got here via Facebook or a LinkedIn post. If you're not signed up for notifications for our technical sessions, you can use this link to register, and then you can just keep up to date with what's happening with new courses and these technical session topics. Emmanuel, do you want to just address Jack's question or Jack's comment,
yeah,
and then also just Don's?
Yes, I see a question mark at the end of that, so I assume it's a question. So question is, can you use the full elastic section modulus to calculate bending capacities of lipped channels and Z sections from the red book if the bending stress doesn't exceed 200 MPa? So for essentially you're saying when using commercial quality purlins, can you use the full section modulus? That answer depends on your sag bar spacing. So if your sag bar spacing is close enough, yes, you can, because the question actually raises two different types of limit states. Remember when we started out, I said there's the limit state of the whole purlin buckling, which I call lateral torsional buckling. And then these class 4 type sections also have another type of buckling that you have to address, which is local buckling, which is essentially a buckling within the shape of the purlin itself. So the answer to your question is, if your sag bars are spaced close enough, then it is possible to assume in some cases that lateral torsional buckling does not occur, and in which case then using the elastic section modulus times stress, whatever the yield stress is legitimate. However, if you are checking for local buckling, I think which is what the question is really about, then it is correct that the shapes that are in our red book, if they are 200 MPa yield strength, meaning they are not high strength steel like 400, 450, 500 MPa, are not at risk of local buckling during bending. So yes, if you use your elastic section modulus for the shapes that we have in the red book, and it's commercial quality steel, it should work. But this comment does not apply to lateral torsional buckling, which is a function of your sag bar spacing. So the answer to your question is yes for local buckling, no for global buckling, which is lateral torsional buckling.
Right, and then Don Garcia's comments. I normally place a sag angle at the knee brace position to provide lateral stability to the purlin, as well as to stabilize rafters when knee braces are used to reduce the purlin span. Do you want to comment on that, Emmanuel?
Okay, interesting. So that's an interesting approach. It probably does work. Some engineers are essentially saying that the knee brace itself also provides torsional bracing to the purlin. So in a sense, they're saying that they don't have to put a sag bar in that location because they're getting restraint for the purlin from the knee brace itself. So I think what you're doing is, in that sense, is redundant, and it's good, meaning it should work.
Right, then just a comment from Simon. Curved roofs, the reduction of Purlin spacings, how much to reduce and the reasons, please.
Curved roofs. So curved roofs are clever in some ways and risky in other ways. So of course, the idea behind curved roofs and why they're clever is if you can actually create an arching action in the roof, because you can then reduce the flexure in your rafter systems. So I'm assuming that the curvature is in the axis of the rafters. That's what I'm assuming here. If you are referring to curvature in the direction of the purlins, I haven't seen a lot of that. And it probably would be very difficult to design simply because most people are not familiar with how to design purlins that are axially loaded. So if we're talking about curving a roof for the purpose of creating arching action to reduce flexure, then the more typical design is to curve the roof in the direction of the rafters. So the effect on purlins is actually it's a moot point in a sense, because it really does depend at the end of the day on the spacing between the rafters. So in that sense, a purlin in a curved roof is designed in the same way as you would design a purlin in an uncurved roof. Now, the other interesting thing about curved roofs, if I have the right image here, is of course that they have a large portion of the roof that is flat. So my comments regarding ponding have to be addressed when doing curved roofs. And like I said, we don't have provisions for that either in our standards nor in our red book. But I do address it in that course that I give.
So Dennis, I'm going to put you on the spot a little bit here. I see that you've already got your mic unmuted, so you must have known I was going to call on you. First of all, do you want to comment a little bit on what Amanuel's just said there, or whatever you wanted to comment on? But then also from the perspective of trends that you've seen in warehouse design from the roofing side, and then maybe some of the challenges that have come up recently.
All right, well, first and foremost, the reason why Purlin centers are reduced on curved roofs, particularly for conceal fix cladding, is that the pan and the bottom of the rib go into compression on a convex roof. And that tends to open the rib slightly, so it loses anchoring action to a certain extent. And most of the manufacturers of the clip-on type profiles reduce the purlins to compensate for that. So that's the main reason for it. The other thing too, of course, is that alignment on a curved roof is very critical, more so than on a conventional flat plane, if you are wanting to avoid fold lines or crease lines where the purlins are. Because if there's a major mismatch between the plane of the top flange of the purlin and the underside of the cladding, A, you're going to get a reduced clipping action, and B, you're going to get crease lines. So that's part of the reasons for reducing the purlin centers for cladding.
Yes, yeah, that's a very good point. And I'll just add there to Dennis's point that that reducing purlin spacing is also the correct way, in my view anyway, to address the additional wind loading that you have at the corners and edges of roofs. So corners and edges of roofs have more wind loading than the middle parts and the top, let's call them the central parts of a roof. That's just how the mechanics of the aeroelasticity of roofs works. And there's always questions about how do you address that? Do you use a bigger purlins, whatever? And I would typically say, no, use the same size purlins, but space them closer to each other. The other area where this might come up, which Dennis somewhat raised last time, is if you have hail or other types of loading that can drift. So by drift, what we mean, and of course snow, if you have snow, which is unusual, but if you have snow, the same thing, is if you have drift kind of loading on roofs, then at least for me, the best way to address that is to space purlins closer to each other, rather than to switch and change purlin sizes.
Okay, Dennis, I just want to come back quickly to some of the changes that you've seen, particularly in warehouse design over the last couple of years. What has been happening from a roofing and cladding perspective?
Well, the biggest problem is that the sag bars aren't put in before access is given for the cladding to be installed, which causes a major problem. But design-wise, there's the constant battle that rages, whether it's lip Z or lip channel. And we notice that designs emanating from the Northern Hemisphere tend to favor the lip Z over the lip channel. I don't know if Manuel would like to comment on that.
Yeah, so I know that we use a lot more lip channels than we do Zs in South Africa. The reason why other jurisdictions may prefer the Z shapes is because they're actually much easier to install, especially when you splice them for continuity. So I don't know if you're aware of how they work, but some of them are quite funky in the sense that they have different flange sizes. So you can literally just stick one onto the other. You don't have to go and create a sleeve section, which you have to do with lip channels, which is of a different shape. So in that sense, they're a very clever technology when it comes to splicing. We didn't address splicing before, but it's a very important topic when dealing with purlins and girts, is how do you actually splice them if you're not going to use simply spanning purlins and girts, if you want some continuity. And we have some details in our red book, but I would say the migration to Z shapes has come, in my understanding, as a result of higher strength purlins being used. These are 450, 550 MPa purlins, where deflection becomes an issue because they're very economical. And of course, one way to deal with the deflection is continuity. And that makes splicing a major issue. And the Z shapes lend themselves to easier splicing.
Good. So if any of you have any more, oh, Dennis, you're still unmuted. Did you have something that you want to comment there?
To further answer your question about modern trends, a factor that is grossly overlooked is the tolerance for out of planeness of purlins. And that upper surface in relation to cladding is again very critical when it comes to conceal fixed profiles to ensure that you're getting a complete engagement onto the clip. And that I think needs to be looked at from the standards point of view of tolerances, because there's no tolerance I'm aware of for purlins and girts in SAISC 2001 series of standards.
Yes,
it's overlooked. It's assumed to be a beam, and in fact, often the alignment can be a lot more critical than you would need for a beam.
Yeah, so we borrow our light profile tolerances from Australia, and we do repeat a few of them in SANS 10162 Part 2 and in the Red Book in I think it's in Chapter 2, where we deal with materials. So we do have some standards, not maybe as extensive as Dennis would like, but they're mostly from Australian standards.
Manuel, I agree with you there. The mismatch is between the 2001 series of standards and the other standards that are enforced.
Okay. So erection tolerances you're talking now. Okay. Yeah.
So I'm just going to launch into my next question. If anyone else has any questions, please pop them in the chat or put your video on and you can ask them in person. Moving on from Purlins and Girts, Amanuel, what are some of the other technical questions that have come up recently that you think have merit in discussing?
Well, very recently, I would say this is, I don't know if it's related to COVID, but this started coming up in the era of COVID, is material supply. This is an issue now that affects purlins and girts, in the sense that the coil out of which these things are made is not as easily available as it used to be before COVID. So I don't know if it's because of COVID that we have this problem, or if it's just a problem that has arisen in the past year and it happens to coincide with COVID. But there happens to be a major shortage of coil in that thickness range that we discussed for purlins and girts. The majority of the coil that is used to make purlins and girts in South Africa is pre-galvanized. It need not be, depends on the engineer's design, but I'm saying that's just the market. And I believe a few of the furnaces at Mittal and were maybe down for a while because of COVID, and maybe import logistics was also disrupted. So I don't know the exact reason, But I do know that the supply was disrupted in the past, let's say 12 to 18 months, and prices have gone up considerably on that type of material. So this is a question that does come up a lot, or a complaint. I don't know which way you put it. And some people have been experimenting with installing purlins from other shapes, non-traditional shapes, on industrial buildings, which I find, of course, to be interesting, because I'm always keen to see new technologies and applications being employed. So I have been involved in one or two projects where the fabricator and engineers are trying to solve the problem of shortage and price by coming up with the different configurations for their purlins and girts.
Okay, so if anyone else has any questions, doesn't have to be specifically related to purlins and girts. It can have anything to do with steel construction. Any technical query that you might have, feel free to pop that in the chat, or to switch your video on. I just want to take a moment to chat a little bit about our Steel Awards. Steel Awards judging for Steel Awards 2022 is taking place in 2021. So if there's a project that you've been involved with that uses steel well or demonstrates excellence in the use of steel construction, if it's been constructed in the last 3 years, it's eligible for Steel Awards 2022. I'm just going to pop a link in the chat for some information about that. And there's a nomination form within there as well. If you'd like to nominate your project for Steel Awards, then you can do so by following that link. Emmanuel, anything you want to say in closing while we see if there are any other questions related to the general use of steel in construction?
Well, just relating to that standard I was referring to earlier, 10162 Part 2, I think it's a good idea for engineers to crack it open, to get it from SABS or from our office if we have stock, and try to look at it, because it also is a useful standard when designing these framed buildings, which are becoming common, like the steel frame buildings, because that's how you design the studs. So it really can open up an engineer's options and architect's options, obviously, for how to frame things, whether building a small hut or a lodge or a large industrial building. So that's a hugely underutilized standard, which is too bad. But our chapter 8 in that red book has been upgraded to reflect the latest one of the latest standard, 10162 Part 2, which is actually not the latest, because the Australians have actually published a few editions since then, but at least the latest South African standard. So that's what I would urge people to do. And if there's anyone here who has tried to crack it open and use it, I'd be very excited. What I do know is even the guys who do light steel framing, they don't really necessarily open it. What they do is they use software. And so it falls on guys like Mike Hall and a few other guys to learn how to use that standard, to check what the guys have done using software, right? Because someone has to check the software. So I would say that's what I would encourage, is to go open that. And of course, start from the chapter 8, which is a very easy introduction to it in the Red Book. You have to get the 2016 version of the Red Book to see the latest provisions. So that would be my general punt.
Great. Okay, so those of you that got here from a LinkedIn link or a Facebook link, or you had a friend send the session information through to you, if you want to find out about updates for our upcoming sessions, I'd encourage you to register on our mailing list for these sessions. I've just put the link in the chat now. It's that type form link. And then also, if you've missed some previous sessions, we do put all of these sessions on our YouTube page, or you can also find them on our website, which would be this link over here that I'm putting in the chat now. If you want to catch up on sessions that you've missed, you'll find them there. If you've got any technical questions or topics that you'd like us to cover in future sessions, please feel free to send an email through to either Emmanuel or myself. It's denise@saisc.co.za, or you can also send it to technical@saisc.co.za. I'll pop that in the chat now. But then we'll be having our next session next week. That will be next week, Wednesday. We're having it today on Tuesday because tomorrow is a public holiday. Have a fantastic day off tomorrow.
Sorry, Denise,
Yes.
I have one more question for Dennis.
Yes, go for
That
it.
I forgot to ask. I don't know if we have a minute.
Yeah, we do.
Okay. What kind of roof cladding metals can you use on galvanized pre-galv purlins? Or is it can you use any metals, or do you have to match purlins and roof cladding?
Good question. No, you can use the aluminium zinc alloys as well as the galvanized based materials on pre-galvanized purlins quite freely, as long as you don't have a steamy atmosphere. If you have a steamy atmosphere, there's a couple of things you have to do.